Okay, let's unpack this. For years, the search for life beyond Earth, it was mostly, well, theoretical, wasn't it?
Absolutely. A numbers game.
But
Possibilities.
thanks, largely to the Kepler mission, we've really shifted. We've gone from asking if habitable worlds exist to asking, okay, what do they actually look like?
We have. We know the galaxy is just littered with planets in the right zones now.
And the sheer volume of data is amazing. We're moving past just finding dots of light,
Right.
right, into really comparing them.
Exactly. That's the key step. We can start sorting the potentially rocky ones, the Earth-like ones, from the bigger, maybe gassy or watery worlds. And crucially, we're understanding the stars they orbit. That's huge.
Absolutely. So today we're diving deep into four of the, let's say, most celebrated potentially habitable exoplanets. These are ones found by Kepler or in follow-ups. We're talking Kepler 442b, K218b, Kepler 186, and Kepler 22b.
Right. And your mission, if you choose to accept it listening in, is really to get past the hype,
Yeah,
the headlines.
I passed the clickbait.
Exactly. Get straight to the hard science. We need to compare what we actually know their sizes, what their host stars tell us, how we found them, and the really big uncertainties. We often call it the atmosphere bottleneck. That governs everything about habitability.
That's the core issue, isn't it? We want those solid nuggets of knowledge. Which of these four very different worlds is, well, the best bet for life based on what we can measure now?
And that brings up a bigger question. What does finding these four orbiting different stars, a G-type like our sun, a K-type orange dwarf, two M-type red dwarfs, what does that variety tell us about how common life-supporting places might actually be out there?
Mhm.
And, maybe more practically, which ones can we actually study today? Like point the James Webb Space Telescope at and get real data, because proximity and size matter a lot for that.
That is the ultimate trade-off, yeah.
Yeah.
The ones that look most Earth-like on paper, they often seem to be the ones just too far away to get a good look at.
Sadly, yes.
So our plan is, we'll look at each planet one by one,
No.
focus on its unique stuff, its pros and cons, its limitations. Then we'll zoom out, compare them, and look at what's next for finding out more. Let's jump in. Okay, here's where it gets really interesting. If you look at any, scientifically credible list of best places to look for life, Kepler 442b is almost always right up there near the top.
It is, consistently.
It's often called the best theoretical rocky candidate, a super-Earth, orbiting a quiet orange dwarf star about 1,200 light-years away. That's quite a distance.
It is a long way off, yeah. But its profile is compelling. It was found using transit photometry. That's the classic Kepler method.
Right, Kepler staring at stars, looking for those tiny periodic dips in brightness when a planet crosses in front.
Exactly. That discovery was announced back in 2015, and follow-up work helped nail down its basic properties.
Okay, let's get those key facts straight. It orbits Kepler 442. That's a K-type dwarf star. So orange, a bit cooler, dimmer than our sun, but crucially, more stable than red dwarfs, right?
Much more stable, generally speaking, yes. It's about 1,200 light-years away, give or take, in the constellation Lyra. Its year, the orbital period, is about 112 days.
How fast is an Earth year?
Much faster, yeah. And it orbits closer to its star, about 0.4 astronomical units. Remember, 1 AU is Earth's distance from the sun.
But because the K-dwarf is cooler, that closer orbit puts it smack bang in the habitable zone.
Precisely. The zone where liquid water could exist on the surface, given the right atmospheric conditions.
You mentioned the K-dwarf aspect is important. Why is orbiting an orange dwarf such a potential plus for habitability?
Well, it's a huge advantage, potentially. These K-dwarfs are incredibly long-lived. They sip their fuel, lasting for tens of billions of years. Compare that to our sun, a G-type star, which has maybe another 5 billion years of stable life left.
So loads more time for life to potentially get started and maybe even evolve complex form.
Exactly. That long, stable lifespan provides this vast cosmic runway for evolution. Stability over deep time, that's potentially critical.
Okay, so stable star, right location. What about its size? That's key too, isn't it?
It's absolutely key. Its radius is measured at about 1.34 times Earth's radius, so 1.34 RL. And its mass, well, that's estimated from models, but it's thought to be around 2.3, maybe 2.4 times Earth's mass.
And that combination, the size and estimated mass, that puts it in a really interesting category. You called it the rocky threshold.
Yes. We see this pattern in the exoplanet data. There seems to be a sort of dividing line somewhere between, say, 1.3 and 1.6 Earth radii. Planets smaller than that overwhelmingly likely to be dense, rocky worlds like Earth or Venus.
Okay.
But once you get bigger than about 1.6 Earth radii, the planet's gravity gets strong enough that it tends to hold onto a thick atmosphere of light gases like hydrogen and helium. It becomes a mini Neptune.
So 1.34 era puts Kepler 442b nicely below that threshold, suggesting it could be genuinely rocky, solid surface.
That's the inference, yes. It makes a rocky composition plausible, unlike the gas-dominated worlds. And its location is great too, right in the conservative habitable zone. It gets about 70% of the starlight Earth receives.
Seems almost perfect on paper. Stable star, right size, right place. But there's always a but, isn't there?
There is, and it's a big one. This is where we hit that atmospheric bottleneck. Its habitability right now rests entirely on assumptions about its atmosphere. We haven't measured it.
And the main assumption is that it needs a pretty thick atmosphere just to stay warm enough.
That's the crux of it. If you calculate its equilibrium temperature, what it would be with no atmosphere, just absorbing starlight, it's only about 233 Kelvin.
Which is cold.
Very cold. That's minus 40 degrees Celsius or minus 40 Fahrenheit, freezing.
So wait a minute. If it needs this massive greenhouse effect, maybe tons of CO2 just to thaw out, and we can't even check if it has an atmosphere, let alone a thick one, is calling it the best bet, based more on its potential from 2015 rather than what we know now.
That's a very fair point. Its high ranking comes from its ideal size and its stable star. Those are great starting points. But you're absolutely right, it needs a significant greenhouse effect. A really substantial blanket of gases, like CO2, would be mandatory to warm the surface enough for liquid water.
And without that thick blanket.
Almost certainly an ice world. A frozen wasteland, despite being in the habitable zone.
And needing that thick CO2 atmosphere might cause other issues too, right? You mentioned potential problems for life, like photosynthesis.
Yes, it cascades. If you need that thick CO2 atmosphere for warmth, that changes the whole environment. Some research suggests the light reaching the surface, what we call photosynthetically active radiation, or PAR, would be less effective for photosynthesis than on Earth.
PAR, that's the specific type of light plants use.
Exactly. The wavelengths plants need for energy. Because the star is a cooler K-dwarf and the planet's far out in the habitable zone receiving less total energy, the light spectrum is different. Less PAR could mean lower biological productivity.
Which could limit complex life. Maybe keep things simple, like microbes.
Yeah.
And maybe mean less oxygen.
That's the potential implication, yes. Less productive photosynthesis could mean low oxygen levels globally, potentially restricting life to more primitive forms. It's all theoretical, based on modeling, but it highlights the atmospheric dependency.
And the real kicker, the frustration, is that even if it is perfect, it's 1,200 light years away.
That's the hard observational limit, the distance barrier. Kepler 442b is just too far, and its star too faint, for our current telescopes, even JWST, to get a good enough signal to analyze its atmosphere in detail.
So we need bigger future telescopes. Decades away, maybe?
Likely decades, yes. We need the next generation of giant ground-based telescopes or dedicated space missions to crack that atmospheric code for distant worlds like this. It's a beautiful candidate, but for now it remains mostly a blueprint locked behind immense distance.
Okay, let's pivot then. Completely different situation with K218b. This one shot to fame, not because it's a perfect Earth twin, it isn't, but because we can actually study it.
Exactly. This is where observation starts to take the lead, even if the picture it paints is, well, complicated.
This is the one where astronomers first detected water vapor in the atmosphere of a planet in the habitable zone, right?
That's the one. A huge milestone back in 2019. Okay, so the basics. K218b orbits K218, which is an M-dwarf, a red dwarf star.
Ah, M-dwarf. We know those come with challenges.
They do. But the massive advantage here is proximity. K218 is only about 124 light years away in the constellation Leo. That's practically next door, astronomically speaking.
Okay, 124 light years. That makes a huge difference for getting a signal for atmospheric analysis. But the planet itself, it blows that rocky threshold out of the water, doesn't it?
Completely. Its radius is about 2.6 times Earth's, and its mass is hefty, around 8.6 times Earth's mass. That puts it squarely in the sub-Neptune or mini-Neptune category. It's definitely rich in volatiles, things like water, hydrogen, helium, not a rocky world.
A very different beast from 442b.
Totally different class of planet.
And it orbits super fast, a 33-day year.
Yeah, whips around its star very quickly. But because the M-dwarf is so dim and cool, even at that close distance, the planet receives roughly the same amount of total energy from its star as Earth does from the sun.
So temperate, potentially, in
Yeah.
terms of energy balance.
In terms of incoming energy, yes. But we should pause on that M dwarf point.
The flares.
The flares. M dwarfs, especially when younger, can be incredibly active, blasting out powerful flares of X-rays and UV radiation. A planet orbiting as close as K2-18b does at 33 days could get absolutely hammered by these flares over billions of years.
Which could strip away its atmosphere.
It's a major concern for M dwarf habitability in general, yes. Could erode or completely remove an atmosphere over geologic time? That's an advantage K-dwarfs like Kepler 442's star mostly avoid.
Okay, so potential atmospheric stripping is a background concern. But despite that, we have detected an atmosphere here. That 2019 Hubble result was big news.
It was groundbreaking. Hubble's transmission spectra looking at starlight filtered through the planet's atmosphere during a transit showed clear signs of water vapor absorption, robust detection of water on a temperate world. Huge.
And JWST, James Webb, has taken that much further since.
Oh, absolutely. JWST's instruments, InterSpec, NIRS, MIRI, they provide much higher resolution and cover a wider range of wavelengths. Multiple teams using JWST data from 2023 into 2025 have confirmed the water vapor and, crucially, detected unambiguous signatures of carbon dioxide, CO2, and methane, CH4.
Wow. CO2 and methane plus water on a temperate world. That sounds incredibly exciting. But again, the size, it's not Earth 2.0. So what's the debate about what this planet actually is?
Right, that's the million-dollar question. Even with this fantastic JWST data, there are basically two main viable interpretations, and they paint vastly different pictures of the planet.
Okay, what's scenario one?
Scenario one is the hazy mini-Neptune. In this picture, K2-18b has a massive, deep atmosphere made mostly of hydrogen and helium surrounding some kind of core. The water, CO2, and methane we detect are mixed into this huge H2-rich envelope, probably along with high-altitude hazes that obscure the view deeper down.
So like Neptune or Uranus, but smaller and warmer.
Kind of, yeah. And if that's the case, any surface would be deep inside under immense, crushing pressures and high temperatures. Absolutely not suitable for Earth-like life on a surface.
Okay, that sounds pretty uninhabitable in the way we usually think of it. What's scenario two?
Scenario two is more exotic. The water world with a high-pressure ocean, sometimes called a Haitian world, though that term implies specific atmospheric composition. This model suggests K2-18b could be covered by a vast, deep, global ocean of liquid water.
An ocean world.
Potentially. But this ocean wouldn't be like Earth's. It would likely be under a very thick, dense atmosphere, maybe kilometers thick, composed of steam or other volatiles, which itself might sit beneath a less dense hydrogen-helium envelope that we're detecting the CO2 and methane in.
So water, but maybe under extreme pressure, beneath a weird atmosphere. Could life exist there?
It opens the door to possibilities, yeah. Maybe exotic life adapted to high-pressure conditions deep in the ocean, or perhaps life in the atmospheric layers. But again, definitely not Earth-like surface life.
The fact that these two incredibly different pictures, a gassy mini-Neptune versus a deep ocean world, can both fit the same high-quality JWST data, that really highlights the challenge, doesn't it?
It perfectly illustrates the complexity of atmospheric retrieval. But that's also why K2-18b is so valuable. It's our best laboratory right now for testing these techniques.
A laboratory? How so?
Because it's close enough and large enough, creating a deeper transit signal, that JWST can get really excellent data. By studying it intensely, figuring out how to distinguish between these scenarios, how to account for hazes, we're learning how to interpret the atmospheres of these smaller, volatile-rich planets.
So the lessons learned from K2-18b will help us when we eventually can study the atmospheres of smaller, potentially rocky worlds.
Exactly. We're honing the tools and models on K2-18b. It's crucial for understanding the limits of our current technology and preparing for the future.
All right, let's move on to another landmark discovery.
Right.
Kepler 186f. This one really made waves because it was the first truly Earth-sized planet found squarely in its star's habitable zone.
A huge symbolic milestone, yeah. Its discovery in 2014 really drove home the point that planets the size of Earth aren't cosmic flukes. They can and do form in the potentially habitable zones of other stars.
And guise-wise, it's the closest to Earth of the four we're discussing today, isn't it?
It is. Its radius is measured at about 1.117 times Earth's radius. Very close indeed. Its mass isn't precisely known, but based on its size, it's likely somewhere between 1 and 2 times Earth's mass. That puts it firmly in the category where a rocky composition is highly probable.
So potentially a rocky world, similar size to Earth. But the catch, the location in the star again.
Right. It's pretty far away, about 490 light-years out in Cygnus. And like K2-18b, it orbits an M dwarf, a red dwarf star called Kepler 186.
Okay, M dwarf again. So potential flare activity is a concern. What else?
The bigger challenges for 186 based on its orbit are likely the amount of light it receives and tidal locking. Let's start with the light.
The dim twilight problem, as the outline called it.
Exactly. Kepler 186 orbits near the outer edge of its star's habitable zone. It only receives about 32% of the stellar energy that Earth gets from the sun, just under a third.
Wow, that's dim.
Very dim. So just like Kepler 442b, without a very substantial greenhouse effect, we're talking a thick atmosphere packed with warming gases like CO2, maybe water vapor, this planet would be incredibly cold.
An ice ball, basically.
Almost certainly, yes. It absolutely requires a powerful natural thermostat in the form of a dense atmosphere to keep surface water liquid.
And it's not just the amount of light, but the type of light too, right? Because it's a red dwarf.
Correct. M dwarfs put out most of their energy in the infrared part of the spectrum, with fewer visible light photons compared to our sun. So the sky on Kepler 186f wouldn't be blue, it would likely appear reddish.
Does that affect habitability beyond just the color of the sky?
It could. The different light spectrum changes the atmospheric chemistry. Photochemical reactions happen at different rates. For example, it might be harder to build up a protective ozone layer, which could leave the surface more exposed to that M dwarf radiation and those flares we mentioned.
Okay, so dim light, potentially problematic light spectrum. And then there's tidal locking. This seems almost unavoidable for planets close to M dwarfs.
It's highly probable, yes. Kepler 186 has a 130-day orbit around its M dwarf. At that distance, the star's gravity exerts strong tidal forces on the planet, likely slowing its rotation over billions of years until one side permanently faces the star.
So one side in perpetual daylight, the other in perpetual night.
That's the classic tidal locking scenario, yes. Eternal day and eternal night.
That must completely change how you model the climate. You can't just talk about a global average temperature anymore.
Not really, no. It becomes a game of extreme temperature contrasts. The climate models get really wild.
Some of the source material described it really vividly, like half this world burns while the other side's ice. Is that a real possibility?
It is. If the atmosphere is too thin or doesn't circulate heat well, the side facing the star could get hot enough to boil away any surface water, while the dark side gets so cold that any atmosphere freezes out, trapping water and gases as permanent ice. A very inhospitable scenario.
So could life even exist in that extreme situation?
It depends critically on the atmosphere. If Kepler 186 has a sufficiently thick atmosphere, and if that atmosphere can efficiently transport heat from the hot day side to the cold night side.
Like a global weather system.
Exactly. A strong atmospheric circulation could moderate the temperatures, preventing the day side from boiling and the night side from freezing solid, if that happens.
Then you get the Terminator line.
Yes, that's the potentially interesting zone. The ring around the planet separating the eternal day from the eternal night. That twilight zone could, theoretically, have moderate temperatures where liquid water might be stable.
A twilight zone where life could potentially gather.
It's a fascinating possibility. Life there would have to be adapted to perpetual twilight, maybe different kinds of photosynthesis or chemosynthesis. But it's a theoretical niche for habitability on a tidally locked world.
But again, the big caveat hangs over all of this speculation.
The same one. Like 442b, Kepler 186 is too far away, its star too faint, for us to currently measure its atmosphere and find out if it has that thick circulating atmosphere, or if it's tidally locked, or if it's just a frozen rock.
So another potentially Earth-like world in size, but locked behind distance and observational limits. Lots of potential, but mostly speculation for now. Okay, let's shift gears one last time to a planet that really captured the public's imagination early on. Kepler 22b. This was announced way back in 2011.
A classic Kepler discovery.
It became kind of a poster child for Kepler's habitable zone finds, mainly because it orbits a star very similar to our own sun.
That was the big deal, yes. Kepler 22b proved that planets could exist in the habitable zones of G-type stars, sun-like stars. Its host star, Kepler 22, is just slightly cooler and smaller than our sun.
And where is it? Also far away.
Also quite distant, yes. Around 630 light-years or so, also in Cygnus, but its orbit is remarkably familiar. Its year is about 290 days.
Almost the same as Earth's year.
Very close, yeah. And that leads to the other really compelling aspect, the amount of energy it receives.
Similar to Earth.
Very similar. If you assume it has an albedo, a reflectivity similar to Earth's, its calculated equilibrium temperature is around 279 Kelvin.
Jeez.
About 6 degrees Celsius or 43 Fahrenheit. right in the habitable zone sweet spot, temperature-wise, based purely on the energy it receives from its sun-like star. So the star type, great. The orbit, great. The insulation,
That's
great.
perfect. So what's the catch this time? It must be the size again, right?
It's the size. That's the reality check that pushes it firmly out of the Earth twin category. Initial estimates were a bit larger, but refined measurements put Kepler 22b's radius at around 2.1 times Earth's radius.
Okay, 2.1 ergo. Let's go back to that rocky threshold we talked about, around 1.6 RAR. 2.1 is definitely bigger than that.
Definitely bigger. It falls on the larger side of something called the radius gap.
The radius gap, what's that?
It's this intriguing feature we see in the exoplanet population. There seems to be a relative scarcity of planets between about 1.5 and 2.0 Earth radii. Planets tend to be smaller, likely rocky super-Earths, or larger, likely volatile-rich mini-Neptunes. There's a gap in between.
And Kepler 22b at 2.1 RAR is clearly on the larger side of that gap.
Correct. Statistically, planets that large are very unlikely to be purely rock and iron like Earth. Their gravity is strong enough during formation that they would have held onto significant amounts of lighter materials, volatiles like water ice, hydrogen, helium.
So even though it has this perfect Earth-like orbit around a sun-like star with Earth-like temperatures, it's probably not a rocky world with continents and oceans like ours.
Highly unlikely, yeah. It's almost certainly volatile rich. The interpretations generally fall into two camps, similar in ways to K218b, actually.
Okay, what are the possibilities?
One possibility is that it's an ocean world. Imagine a planet with a much larger fraction of its mass as water compared to Earth. It could have a very deep global ocean, maybe tens or hundreds of kilometers deep, potentially sitting on top of exotic high-pressure ice phases deep down.
A true water world. But would it have a surface we could stand on?
Probably not a solid surface like Earth's continents. And even the ocean surface might be under a very thick, dense atmosphere, perhaps mostly steam or other volatiles under high pressure.
Okay, what's the other scenario?
The other main possibility is the mini-Neptune model. In this case, it would have a relatively smaller rocky or icy core, but it would be enveloped in a very thick, deep atmosphere, maybe hydrogen and helium dominated, or perhaps a thick envelope of supercritical water or steam.
Supercritical.
A state where there's no distinct liquid or gas phase, just a dense fluid. In that scenario, there wouldn't be a defined surface at all. You'd just descend into an atmosphere that gets denser and hotter with depth.
So the bottom line for Kepler 22b is fantastic star, fantastic orbit, great temperature, but its large size means its actual surface conditions are completely unknown and likely very un-Earth-like. It all depends on how much volatile stuff it has and where it is.
That sums it up perfectly. If somehow it only had a thin, moderate, Earth-like atmosphere, its climate could be quite pleasant because of the Earth-like insulation, but a thick, volatile envelope, which is much more likely given its size, would lead to very high surface pressures and temperatures, nothing like Earth.
And like the others, apart from K218b,
It's too far away, over 600 light years. Its historical significance is huge, proving habitable zone planets exist around sun-like stars. But detailed atmospheric study, that's beyond our current reach. Its true nature remains unknown.
Okay, so we've looked at 4 really different worlds, all technically in the habitable zone. Kepler 442b, K218b, Kepler 186e, Kepler 22b. What does it all mean when we put them side by side? It feels like a real spectrum of possibilities and problems.
It really is a spectrum. Let's quickly recap the key differences based on what we've discussed.
First up, size and the potential for being rocky. We've got 2 contenders there, right?
Right, Kepler 186 is the most Earth-sized at about 1.17 Uri, and Kepler 442b is close behind at 1.34 Ur. These are the two that fall nicely below that 1.6 Ur threshold, making a rocky composition plausible, even likely.
Then you have the bigger ones, the ones that likely cross that radius gap into volatile territory.
Exactly. K218b is significantly larger at 2.6 Ur, and Kepler 22b is around 2.1 to 2.4 Uri. These are almost certainly mini-Neptunes or deep ocean volatile worlds, not terrestrial planets in the Earth sense.
Okay, next, the host stars. This makes a huge difference too.
Massive difference. Kepler 22g has the ideal star from our perspective, a G-type, like our sun. Stable, familiar spectrum, but it's far away. Kepler 442b orbits that stable, long-lived K-type orange dwarf. That's maybe the sweet spot for long-term evolution, potentially.
And then the other two orbit M dwarfs, the red dwarfs, Kepler 186f and K218b.
Which brings in the challenges we talked about.
Right.
The dim light requiring planets to huddle closer, the risk of intense stellar flares stripping atmospheres, the different light spectrum, and that almost unavoidable issue of tidal locking for close-in planets.
And finally, the crucial point, observational status.
Yeah.
What can we actually measure today?
This is where the picture gets really clear. Only K218b has yielded significant atmospheric data so far.
Why only that one?
It's that combination of being relatively close, just 124 light years, and being quite large. A larger planet blocks more starlight during a transit, creating a stronger signal that telescopes like Hubble and especially JWST can analyze effectively. That's how we got the water, CO2, and methane detections.
And the other three, the potentially rocky ones, 442b and 186, and the sun-like star 122b.
They're just too far away, and in the case of 186 and 442b, orbiting relatively faint stars. The signal from their atmospheres passing in front of their stars is too weak for even JWST to pick out detailed molecular signatures right now. We can't probe their atmospheres yet.
It's worth quickly recapping how we know even the basic stuff, because that really underlines the limitations. All four were found by Kepler using transit photometry.
Right. Transit photometry is great for finding planets and measuring their radius and how long their year is. It's the discovery workhorse.
But it doesn't tell you if it's made of rock or gas. For that, you need the mass, right, which gives you density.
Exactly. Mass is key. And the primary way to measure mass is the radial velocity method, or RV.
Watching the star wobble as the planet tugs on it.
Precisely. But RV is really hard, especially for small planets orbiting far from their star, or planets orbiting faint stars like many of the M dwarfs and the distant stars Kepler looked at. That's why the masses for planets like Kepler 186 and Kepler 22b are still uncertain or just estimated based on radius. Getting precise masses for these distant, smaller worlds is a huge challenge.
And if mass is hard, getting the atmosphere is even harder. That's the transmission spectroscopy you mentioned with Hubble and JWST.
Yes. We watch starlight filter through the thin ring of the planet's atmosphere during a transit and look for the telltale fingerprints of molecules absorbing specific wavelengths of light.
JWST has been a game changer there, obviously, giving us the CO2 and methane on K218b. But you also mentioned model degeneracy. Even with the best data, it's not straightforward.
Not at all. Model degeneracy is a fundamental challenge. It means that sometimes different underlying physical scenarios inside the planet or in its atmosphere can produce very similar observable signals, similar spectra.
So for K218b, a deep hydrogen atmosphere with high clouds could look spectroscopically similar to a world with a lower-lying ocean surface hidden beneath a different kind of hazy or cloudy upper atmosphere.
That's the gist of it, yeah. High-altitude hazes are particularly problematic. They can scatter starlight and mute the molecular signals coming from lower down, making it really hard to be sure about the structure and composition deeper in the atmosphere. We can confidently say there's water, there's CO2, but figuring out the exact atmospheric profile, the pressure at different layers, whether there's a surface, that's where the models still struggle to give a unique answer.
So K218b is giving us amazing data, but it's also teaching us just how hard interpreting that data is, especially when hazes are involved.
Exactly. It's pushing the science forward. It's the perfect, albeit complicated, test case for refining our techniques before we can eventually apply them to the fainter signals from potentially rocky worlds.
So bringing it all together, this deep dive really underscores a fundamental challenge, doesn't it? For the planets that seem most Earth-like in size, maybe orbiting the right kind of stars like Kepler 442b, maybe Kepler 186, their actual habitability depends entirely on an atmosphere we simply cannot measure yet.
That's the bottleneck. Distance creates this chasm between potential and proof.
And this leads to that interesting tension you mentioned that the source has highlighted, a conflict between the cold, hard data and, well, human hope or ambition.
It does. You look at the data for, say, a tidally locked world like Kepler 186, the numbers tell you about the extreme temperature differences, the potential for atmospheric freeze-out or boiling, the risk from stellar flares. The physics often suggests a very challenging environment for life as we know it.
But the source material contrasted just looking at those numbers with believing in a miracle, maybe not literally, but the miracle of life's tenacity or human ingenuity or just the drive to find something out there.
Exactly. That contrast really captures the spirit of exoplanet science. We see the immense hurdles presented by the data, the need for a perfect atmospheric circulation on a 186F to make the Terminator habitable, the huge greenhouse needed for 442b. Yet the ambition persists. The drive to find life, maybe even a future home, makes us focus on the possibilities, even against steep odds.
It's that difference between seeing a world where half burns while the other side's ice, and focusing instead on that narrow Terminator line as a potential haven, however unlikely it might seem based purely on the physics.
Precisely. And the implications of something like tidal locking go beyond just climate. Even if that Terminator zone is habitable, surviving there would require radical adaptation, either biologically or technologically, for colonists. It's not just Earth, but with a weird sky. It's a fundamentally different kind of planetary environment. The data presents the challenges. Human aspiration keeps pushing us to find solutions or exceptions.
So looking ahead, how do we bridge this data chasm? What are the concrete next steps to get past speculation, especially for those distant rocky worlds?
Well, first, we keep pushing JWST to its limits. Continued observations of K218b are crucial to try and chip away at that model degeneracy. Can we better constrain the hazes, maybe get hints of other molecules that favor one scenario over the other? Refining our understanding of these volatile-rich worlds is essential groundwork.
But for the truly distant, potentially rocky ones like Kepler 442b or 186F, JWST alone won't cut it.
Likely not for detailed atmospheric characterization. For those, we need the next generation of truly giant telescopes. On the ground, we're talking about the extremely large telescopes, the ELTs, with mirrors 30 meters across or more. They'll collect vastly more light from these faint, distant systems.
And in space.
In space, the long-term goal is dedicated direct imaging missions. Telescopes equipped with highly advanced coronagraphs or star shades designed specifically to block out the blinding light of the host star, allowing us to directly see the faint light reflected from the planet itself or even its thermal emission. That's the technology we need to finally analyze the atmospheres of Earth-sized planets orbiting sun-like stars hundreds of light years away.
So decades of work still ahead.
Definitely. But the path is becoming clearer.
We've journeyed through 4 fascinating worlds today, all in the habitable zone on paper, but each wildly different. The potentially stable rocky super-Earth, 442b. The close-in, complex mini-Neptune we can actually study, K218b. The dim, potentially locked Earth-sized world around a red dwarf, 186F. And the big volatile planet in that perfect sun-like orbit, 22b. It really shows the universe is brimming with possibilities, but pinning them down, measuring them, that's the monumental task.
It leaves us with a really provocative question, I think. A kind of strategic dilemma based on capability versus desire. If we had limited resources, limited telescope time today, where do we focus our most intense effort?
Do we prioritize the nearby, non-ideal world like K218b, the one we can characterize, even if it's a mini Neptune or a weird ocean world, because we can learn so much about planetary atmospheres from it?
Or do we hold out hope, keep modeling, keep searching for ways to study the distant, potentially perfect rocky twin like Kepler 440db, the one that truly matches our ideal, even though it remains stubbornly beyond our observational grasp for now?
It really boils down to more than just, is it habitable? It's also, can we get the data? And maybe even, eventually, could we survive there? Whether you put your faith in the challenging numbers or hold out hope for some kind of cosmic miracle.